Om Sri Guru Basvalingaya Nama. Well, in the last period, we had seen the topic transformer, its construction, then power losses in transformer. Today, we shall see what are chokes. Chokes. Well, actually, in tube light and many places like the street lights will be using a coil to control the flow of AC. Those things are called as choke. Well, what will be, how it will be is, its shape will be like this. That is, we will be taking an inductance coil. This inductance coil should have very low resistance and it should have only inductance. So, such a coil is called as choke, and what for it is used? To control the flow of alternating current. Well, what you will find that this will be not effective in DC circuit. Why? Its resistance will be very small or negligible, that is equivalent to 0. So, in such a case we cannot control DC using choke, but alternating current, as the current will be changing its direction periodically. Because of that, the magnetic flux linked with the coil changes periodically. Because of that, it will be opposing the flow of alternating current. So, therefore, to control the flow of AC, we make use of these chokes. Well, now here we will be having two types of chokes. One is called low frequency choke and other is called high frequency choke. Now, what we do for low frequency choke? For low frequency choke, it is also called as LF choke. LF choke, well, we consider a value of inductor of large value. So, a coil of large inductance is taken, and now what is done? Since the value of inductance is large, therefore, we require inside this choke one supporting medium, and this core is taken of soft iron. Well, now here what is the meaning of low frequency choke? This choke or this coil will allow only high frequencies to pass through it and cuts low frequency signals. That is what is there. Low frequency choke means cut. So, it cut or blocks low frequency signals and allows only high frequency signals to pass through it. Whereas, now if you take high frequency choke, it is also called as HF choke. HF choke. Well, now what we do here? We take an inductance coil of low self inductance, and now since inductance coil is of low self inductance, here if we take a core, then problem will arise. Therefore, what we do? We keep the coil as it is and we will have air in between. So, we take here air as a medium between the choke. So, that is why it is called as air core choke and it is called soft iron core choke. Now, what it does? High frequency choke cut high frequency signals. Well, name itself is there, high frequency cut, and allows low frequencies to pass through it. Well, now we know that whenever we have got a coil, it will have some value of inductive reactance, and that can be given by the formula XL equal to omega L. And now we know one more thing, that the current, the phase difference between current and voltage in case of the inductor is current will be lagging behind the voltage by 90 degree. Current will be lagging behind the voltage by 90 degree. As the phase difference is 90 degree, what we will find out? It is for VL. So this difference is how much? 90 degree. So power loss can be given by formula Vrms into Irms into cos of phi. Cos of phi. Now here phase difference is how much? It is phi. So if we have got only pure coil whose resistance is not there, then what we will find that Vrms Irms into cos of 90 will be there, cos 90 will be how much? 0. But actually we cannot think of a coil without resistance. So even if we take a conducting material like we will be taking here for making the core, copper wire, so that will be having small value of resistance, and because of small value of resistance we will find that average power loss will be small finite value, it will not be 0, but it will be very less. Now why we take only inductance, means why we take only choke, not resistance to control the flow of AC? Well, for that if we take the formula for power, power loss, we have got power loss formula to be this, and if we take resistance, in resistance current and voltage will be in phase. Current and voltage will be in phase. Will write the IR, so they will be in phase. As they are in phase, angle phi is 0, so we will be having Vrms into Irms into cos of 0. It means it is much large, or we can also write down this as Irms square into R will be the value of power loss. So as compared to this loss will be much larger. That is why we do not make use of the resistance to control flow of AC, but instead we take the coil, choke coil or inductance coil to control the flow of alternating current. Now let us go for the next topic, that is LC oscillations. LC oscillations. Well, what we do? We take one capacitor and one inductor, connect them in series like this, and to charge the capacitor we make use of one battery, and a key will be there. Actually we can take the key here also, one key and one key over here. Suppose say in the beginning this is connected, capacity is C and the inductance say is L. So inductance is L, capacitance is C. If we connect the battery to the capacitor, then depending upon the voltage supplied, the capacitor will be charged. Say here we have got negative charges Q, and here positive charges Q will be obtained, and potential difference will be how much? Say V. V is the potential difference obtained here. Now after charging we open the first key. We open the first key and close the second key. Now what is been found? If suppose inductance coil has got no resistance, that is resistance of the coil is 0, then what happened? Now here the charge starts discharging. Even if it is not 0, charge will be discharging. We will talk about that 0 or non-zero of resistance later also. Now presently as soon as this key is closed, the charges start discharging. So what happened? A current starts flowing through this inductor. Now, as the time increases, the flow of current increases. Now, here what will happen? We know that voltage can be given as VL equal to minus L into di by dt. And here, because of current, what should happen? Energy will be developed here. Well, initially how much of energy was developed or stored in the capacitor? We can write down that one as energy stored in capacitor as Q square divided by 2C. We shall write down this one little later. Now, so energy stored in the capacitor is Q square by 2C. Well, now as the current starts flowing through the inductor, here magnetic energy will be developed, and that magnetic energy can be written as half minus half L into I square. So, if we leave the magnitude, we can write on as only half L I square. So, now here I is what? When capacitor is fully discharged and maximum current is flowing through the inductor, then the energy stored here will be half L I square. What does the minus sign indicate? That here, as the current is flowing through the coil like this, in this one reverse EMF will be induced. That's what is given by minus L into di by dt. And so it means here the EMF will be developed, that EMF will make a current to flow, that current will be flowing in which direction? In the opposite direction, and that is what is denoted by this minus sign, and over here also. So now what is been found that when the energy of the capacitor is completely discharged, then that energy will be stored in the inductor in terms of what energy? Magnetic energy. So if we draw graph for variation of energy for capacitor and inductor. So capacitor energy time, inductor energy and time. So what we will find that initially capacitor will be having maximum energy, inductor will be having zero energy. So as capacitor starts discharging, the energy of the inductor goes on increasing, and at the moment when energy of the capacitor becomes zero, the energy of the inductor becomes a maximum. Now what happens? There is no more charge, since capacitor has completely discharged. There is no more charge here. So what should happen? The current flowing in the inductor starts decreasing. As the current flowing through the inductor starts decreasing, according to Lenz's law, an EMF will be induced in the coil. That EMF will induce a current to flow. How the current flows? It flows to oppose the decrease in current. Here current was flowing like this, it is decreasing. So here now what should happen? A increasing current will flow. It means current flows in this manner. And because of that, upper plate gets charged by positive charges and lower plate gets charged by negative charges. So here we will be having this as a case. So now when the current becomes zero, it will be fully charged by plus Q charges, it will be completely charged by minus Q charges. That is, energy of the capacitor again becomes a maximum, and energy of the inductor becomes a zero. So now we can show that one, that energy of the capacitor, since capacitor in the beginning had this plate positively charged, now it is oppositely charged. Hence we can show that one like this, that capacitor will be having the charge in the opposite direction, inductor has lost its complete energy. Now, again what happens, this phenomena repeat. After this, current starts flowing in the reverse direction. Now, current starts flowing in the reverse direction like this. So, because of that, here we will find that magnetic energy will be obtained. So, as the rate of flow of charge goes on increasing, current through this becomes maximum. So, when the capacitor is completely discharged, it will be having energy in the inductor in the form of magnetic field, which is 1 by 2 Li square. So, now we can show that energy in the inductor will be maximum. Capacitor has got discharged completely. Capacitor has got discharged completely. Well, now, why we are showing this one in the downward direction? Because here as the current is increasing like this, in this one EMF will be developed. That EMF will be opposing it, hence a current will be induced in this to oppose it. So, that is why we are shown this graph to be in the downward direction. Now, again when the capacitor is completely discharged, there is only energy in the form of magnetic field here. So, now as there is no more charge to come, hence the current starts decreasing. As the current starts decreasing, what should happen here? This current is increasing, one EMF will be developed. Because of this current decreasing, one EMF will be induced. This EMF will make the current to continue in the same direction, and because of that, we will find that now the capacitor will be charged again in the initial manner how it was, that is this plate becomes positively charged, upper plate becomes negatively charged. So, this means what? We will be finding that capacitor has got charged by same amount of energy as in the beginning, and energy of the inductor has become 0. So, this phenomena will be getting repeated again and again. This process will be getting repeated again and again, and these oscillations only are called as LC oscillations. Now, what is the frequency of this LC oscillations? Can be obtained from a relation. Well, here what is the potential difference obtained? That is, we can write down as Vc, and potential difference obtained here can be written as VL is equal to what? 0, because after this is charged, cell is not connected to this. Because of that, we will find that here total amount of potential difference, net amount of potential difference must be 0. But for capacity, we know that Q is equal to C equal to Q divided by V, and inductor, how much of voltage is induced is given by minus L into di divided by dt. So, if we write the two things here, this is nothing but Vc, so Vc equal to Q by C. Q by C minus L into di by dt is equal to what? 0. Now, di by dt, we can write down di by dt as what? D by dt into I is nothing but rate of flow of charge, so dq by dt. Rate of flow of charge, that is nothing but d2q by dt square. So, if we write down here, we get Q by C minus L into d2q divided by dt square equal to 0. Now, what we will do? We will take we will divide throughout by C, we will divide throughout by L. So, we can write down this one as minus L minus d2q. First, I will do like this. So, first we will divide throughout by L. We get Q by LC minus d2q by dt square equal to 0. if we write it reverse, means if we take this one that side, we get d2q by dt square minus 1 by LC into q equal to what? 0. So, it is equation number 1. Now, it is in the form that d2x by dt square minus omega square x equal to 0. That is equation of oscillation, CR equation of simple harmonic wave. So, now if we compare the two, what we get? Omega square equal to, we get 1 by LC. So, we will be having here omega square equal to 1 by LC. So, omega equal to, we get 1 by root LC. So, this is the equation for angular frequency of oscillations of the LC circuit. Now, we know that omega is equal to again 2 pi f. So, because of this, we can write f equal to 1 by 2 pi root of LC. So, this will be the equation we will be getting for the oscillations, the frequency of oscillation of LC circuit. Now, what we will find that if suppose the resistance of the coil is 0, means if the connecting wires do not have any resistance, even inductance has got no resistance, then what you will find that the oscillations obtained will be continuous and their magnitude also will remain same. So, continuously we will be getting this, and this type of thing is called undamped wave or undamped oscillations. Means what? Amplitude is remaining same throughout in this type of oscillation. So, such type of thing is called as undamped oscillation. Now, but sometimes what we will find that the resistance, this connecting wire or the inductor coil may have small resistance, and because of that what happens, the oscillations are found to be like this in nature. Like this in nature means what? Its amplitude will be going, the amplitude will be decreasing continuously. Now, this type of oscillations are called as what? Damped oscillations, and this will occur because of resistance of the wire as well as the resistance of the inductance coil. So, now here, well, frequency, for frequency we can use this formula, for angular frequency we can use this formula and calculate the value of it. Now, here the chapter is completed, but we have seen earlier series LCR circuit. For our competitive exams, sometimes questions may be asked from parallel resonant circuit or parallel LCR circuit. Now, well, here what you do? Series LCR circuit, first I will write on its important thing, and no need to remember extra over here. Just from that comparison we can obtain equations of this. Well, suppose say that we have got a resistance, a inductance and a capacitor connected in series in this manner. I had mentioned earlier R, L and C. Here VR was the voltage, VL was the voltage, VC was the voltage here. Here applied voltage is V0 sin of omega t. So, we will learn the terms here. Well, what? First one, formula for VR was what? I0 into R. Second one, VL was I0 into XL. Third one was VC equal to I0 into XC. I0 into XC. Well, then we had written our equation for what? Voltage, net voltage, that is V0 equal to under root of VR square plus VC minus VL square. Then had written equation for impedance Z equal to under root of R square plus XC minus XL square. That similar things will be obtaining here. So, just if we forget also, we can remember from this that conditions for parallel LCR circuit. Parallel LCR circuit. Now, here what will be having? An AC source will be connected to all those three things. One is resistance, one is inductance, and one is capacitor. Say C is the value of this, L is the value of this, R is the value of it. Now, what happened? We will be having, say it is V equal to V naught sin of omega t is the equation of voltage applied. This will send one current, say how much? I. Now what happen? It will send a current to this, that is IR. One current, because all the three are in parallel, so you can say IL and here IC. Now, there we are written equations for voltages. Here we will be writing the equations for current. So, this can be written as first IR is equal to voltage across R divided by resistance. So, here voltage is how much? V. We can write on V divided by R. If we go for amplitude, then we can write on V naught. Instantaneous V, amplitude V naught. Since here also we are written as I naught, I will talk in terms of amplitude itself. So, IR equal to what? V naught divided by R. So, here VR equal to I naught into R was the thing. Same manner we get on IC. IC is equal to V naught divided by XC, because capacitor will be having capacitive reactance. Then third one is IL is equal to V naught by XL. Now, here we are written as V naught equal to so much. Similar manner we will be writing here equation for current. So, how we write? We write on here I is equal to, or I naught amplitude, I naught equal to under root of I R square plus IC minus IL whole square. Now, you can see here IR is there, IR is V naught by R. So, V naught by R, here we will be having IC is V naught by XC, IL V naught by XL. V naught can be taken out. This can be written as I naught equal to V naught divided by Z. I naught can be written as V naught by Z. So, we can write that impedance formula as 1 by Z is equal to under root of, here we will be having 1 by R square plus 1 by XC minus 1 by XL whole square. So, we will be having here this as the formula corresponding to that. So, you can remember there we will be writing V naught, in series we will be writing V naught equal to under root of VR square plus VC minus VL square, and here we will be writing in terms of current as I naught equal to root of IR square plus IC bracket IC minus IL whole square. Terms are similar. So, now the impedance there was Z equal to so much. Now, here we will be having 1 by Z equal to 1 by R square plus 1 by XC minus 1 by XL whole square. Suppose say forget, put the value of I naught as how much? V naught by Z, and IR value substitute here, IC value substitute here, and take V naught and cut that one, will be getting this equation. So, we have got these as the things for it. Now, next condition for impedance here, condition for resonance circuit, for resonance is what? VL must be equal to VC. Now here condition for resonance will be IL equal to IC. IL equal to IC. Now there we have obtained a formula for angular frequency of resonance circuit as 1 by root LC, or in terms of frequency we have obtained as 1 by 2 pi under root of LC, 2 pi root of LC. So here also you will be getting the same IL equal to IC. If you put IL equal to IC, V naught cancels, 1 by X equal to 1 by XL, we get it. So 1 by XC, I will just derive here. This is the condition, that is IL equal to IC, IL is equal to V naught by XL equal to V naught by XC, cancels, so XL equal to XC only will be having. And as XL equal to XC is obtained, therefore what should happen? Here also I can write on, or in terms of resistances of capacitor and inductor, that will become so much. So this formula is obtained, therefore naturally we will be having same formula to come here, 1 by root of LC, or F equal to 1 by 2 pi root of LC. Now here what we will find that in this case what we had obtained, as the frequency is gradually increased, current was increasing and was maximum at one frequency, that is called as what? It is resonant frequency F naught. At that we are having maximum current to flow through the circuit. Now here what we will find? We will find the opposite of that, as we vary the frequency of parallel resonance circuit, then we will find that current starts decreasing, it becomes minimum at this frequency, that is resonant frequency, and then current increases. So if you remember this few formula, it will be sufficient for us to do the questions of a parallel resonance circuit. Now we shall go for some numericals. Well, now because of some problem not able to show that one on the chart, well I shall write this question on the board. A transformer steps up an AC voltage from 230 volt to 2300 volt. If the number of turns in the secondary coil is 1000 of turns, turns in the primary coil will be well, here we will not write the options, right. What is given? Transformer steps up an AC voltage from, it means it is primary voltage, it is Vp, and it is secondary voltage, that is Vs. Well, if the number of turns in the primary coil is 1000, that is it is Np. The number of turns in the secondary coil, number of turns in the secondary coil means Ns. Then the number of turns in the primary coil means Np equal to how much? It is a simplest question. Well, so solution what? Here we have got formula Ns by Np is equal to Vs divided by Vp. Now, Ns is given to be equal to 1000. Np not given is equal to Vs is 2300 by 230. This cuts by 10 cuts, we will be getting here Np equal to how much? 100 turns. 100 turns. But now let us go for next question. Next question. Well, suppose say that, well, it is mentioned the transformer ratio of a transformer is 5. If the primary voltage of the transformer is 400 volt, comma 50 hertz, the secondary voltage will be, the secondary voltage will be here. Options are required because options are given in frequency way also, so we will write down that one. So it is 2000 volt 2000 volt 250 hertz. Second one 80 volt 50 hertz. Third one 80 volt 10 hertz. Fourth one 2000 volt and 50 hertz. 50 hertz. So well, now for the solution. Well, what is given? The turn ratio of transformer is 5. Well, if you remember, I mentioned turn ratio is what? Ns by Np is given to us equal to how much? It is equal to 5. Ns by Np. And primary voltage of the transformer means what? It is Vp. Vp equal to 400 volt. What is us? Secondary voltage means Vs equal to question mark. We can use the same formula, we will write it reverse. Vs by Vp equal to Ns by Np. Ns by Np. Now it will become Vs equal to Ns by Np into Vp. Ns by Np is 5 into 400, that is 2000 volt. But along with that, what is given here? Frequency also is mentioned. So now here a transformer only steps up the voltage or steps down the voltage, but it will not change the frequency. Therefore, frequency will be how much? 50 hertz itself, and that's why answer is which one? Answer is fourth one. Well, now we'll come to the next one. The transformer ratio of a transformer is 10:1. 10:1. The current in the primary, the current in the primary circuit the current in the primary circuit if the secondary current required is 100 ampere, assuming the transformer to be ideal, comma, is, well, what is given here? The transformer ratio of a transformer is 10:1. Transformer ratio means what? Ns divided by Np value is given to us is 10:1. The current in the primary circuit is, it means Ip is equal to how much is asked, and if the secondary current required, it is Is. This is Is, and we know that Ns by Np is equal to Vs by Vp is equal to Ip divided by Is. So now we'll use this identity to solve it. We get it on here that Ip is equal to Ns by Np into Is. Ns by Np into Is. Ns by Np is how much? 10/1 into Is is how much? 100. So this is 1000 ampere will be the answer. 1000 ampere. Well, now today here we stop. Tomorrow we'll do 2 or 3 numericals, then start with the new chapter.